Hello, I'm Fatima, and today we'll have an introduction to linear algebra. So, we all know what linear algebra is, right? I'm not going to teach you algebra here. Rather, I will show you how they are being used from the aspect of machine learning. So, enjoy. Before starting, I would like to answer the question why linear algebra is important. Okay, so to answer this, first I would like you to recall about the common example we use to build a model in machine learning, the house pricing example. And for those who still doesn't know about this, just imagine we have some informations here. Okay, some inputs. It could be area, then number of rooms, then square feet. Area means location, and then the size of the house in square feet, and these things basically will determine the price. Okay, so suppose we have the location is USA or New York. This is New York, and the number of room 4 maybe, and square feet is what can I say, it could be any number, and based on this the price is 45k maybe. Okay, this is anyways $45k. So we may have a lot of informations here. Okay, not just one but 2, 3, 4, anything. Based on these inputs we determine the price, and here yes, each input is a number or a list of number. Okay, as the location, these names will eventually be converted into numbers, and these numbers form a vector. If there are two features, it's 2D. As you can see, we have three features here. Feature 1, we have three features here. This is a feature, this is another feature, this is another feature. So this is a 3D vector, and vectors can be represented as dimensions. So linear algebra is effective with high dimensional data. This is a 3D data, right? We human, our capacity is 3D only. We cannot visualize a 4D image, a 4D vector. Okay, but what if we have something, a dataset or a vector that has not 3 but 300 features? So in that case, what will we do, right? So you can apply dimensionality reduction here, which is a PCA, and this is where linear algebra becomes very, very crucial. You can just apply PCA to convert them all those 300 features in just 2 dimensions, and at the end of the day everything is going to be turned into vectors. Moreover, in machine learning, linear algebra is highly used to train a model, because in model training we have to perform a lot of matrix operations. In dimensionality reduction, PCA is used based on linear algebra, which is eigenvalue. We'll talk about that later. And in neural networking, forward propagation and backward propagation, matrix operation is heavily intensively used here. Okay, so enough with the introduction. I think now we will able to move to our main topic. Okay, so first of all, we will start with scalars and vectors. Okay, so what is scalar? A scalar is just a numerical value, represents a magnitude or a quantity, and vector is another numerical value which has both magnitude and a direction. In data science or machine learning, a vector doesn't necessarily mean an object with a physical direction like in physics. Instead, it represents a collection of values. It can have different dimensions like where is my pen? It can have different dimensions like 10, like 20 and 30. This is a 3D representation. Okay, and we can even plot this into the graph also. And okay, so let me give you an example. So a student IQ, what should I IQ, and then we have number of study hours. Number of study in hour. Okay, so the IQ is maybe 40. Number of study 3 hours. And then what could be the result, pass or fail, right? If IQ is 40 and number of study is 3 hours, then definitely it's going to be a fail, right? It is a fail. Then if the IQ is 90 and okay, let me turn this into 19, and this should be 100. That should do the work. This is 100, and number of study is 3 hours. Okay, 2 hours. This is also 2 hours. So yes, this person is going to pass the exam. So this is just a vector representation. This is a vector. This is another vector. We have two vector here with two features, and this we can represent them in a graph. Okay, let me draw a graph here. No, I need line. Where is the line? Yes, another line. This is okay. This is the line. This is interesting, by the way, so listen carefully. Okay, so this is the pass and the fail. We are going to determine this with 1, 0 and 1. 0 means fail, 1 means pass. Okay, so the first for this person, the x is going to be 19, and the y is 3, not 3, 2. The y is 2, and for this one the x is 100, and this is the number of study is 3. So let me write it here: 19, 92, and for the second person it is 103. Okay, and look at this graph here. Let me start with 80, 90, 100, 110, and over here 1, 2, 3, 3, 2, 1. Okay, good. So if I plot these points here, okay, if I plot these points here, 90 and 2 here, this is for the student who failed. Okay, and for this student, for the second student who passed, this is 100, 100, and there we have 3. Okay, good. Let me change the color. I need to differentiate them. This is the this is the person who passed the exam, and this is the person who failed the exam. So we'll have, if you know about the linear regression, we'll have some kind of linear equation here, a straight line that will differ between them. This is a straight line. Now, interesting fact is, we can have here we have just one, like two, we have two persons, right? But we can have more, we can have many more, right? We can have 100 students here. So as I have divided this part here, this is for the pass and this is for fail. Okay, what's happening here? This is for fails. If a point that goes here, of course there will be many points that will be placed here, and there will more points that will be placed here. Okay, so if this is a point, if a point is here, what will our model tell? That this person has passed the exam, right? And if a point is here, our model will predict that this person has failed. Okay, so this is a model that is totally built on vectors. Have you noticed this? That these numbers, they're actually turning into vectors, and then we made a model. Like, no, we really didn't made a model, but this is the concept here, right? This is the concept. And at the end of the day, we all have just a model where we have to input like features, and then we'll get output, and this thing is totally based on vectors. Any kind of vector, another, like, what can I say, the gaming industry relies heavily on vectors. Okay, if you're into gaming, let me talk about the GTA. Okay, so just imagine you are driving a car at, no, I'm going to move from here. Imagine you have a car and sorry, in GTA you are riding a car at where's the rubber? I'm sorry. Yes, this is a car that you are riding. Okay, you are driving like in 200 kilometer per hour. You did some kind of thing and you have a threat situation or whatever, and on the other hand you have police chasing you. Okay, they're chasing you in 100 kilometer per hour. So what will happen if you both collide? If you collide, some kind of some kind of effect will happen, like your car, it could move 100 times, it could spin 100 times, it could crash, or maybe there could be a fire or whatever, anything can be happen. Do you know how this is, what's the reason behind this? It is vector, not just vector, it is unit vector. The unit vector is same thing. This is my graph. Where is the x-axis? Yes, this is my x-axis, and the unit vector is 1 2 3 4. 1 2 3 a 3 3 3. Okay, 1 2 3 here. This is my okay, this is my roughly drawing. So this is a 3,3 point, and this is you of course know about the unit vectors, right? 3I plus 3j. Okay, so these i's, these j's, and we have another that is k cap. These are called the unit vectors. These are the unit vectors, and these vectors are behind the effects, like the car might explode, catch fire, then those effects are derived from these unit vectors. Let me give you another example. Like in GTA, you have the option of a boat, right? Imagine you are riding a boat, and there these are the waves, and your boat is representing a vector, and this water, this is also another vector. So when your boat goes this way and then the water is this way, then they crash, they collide, and some kind of like the boat will jump higher or the boat will stay straight. Everything, this all comes from these unit vectors. So these effects are all derived from vector units. These are just some example, and I hope you understand why vectors are important. You know about the vector multiplication, right? Like as I said, I'm not here to teach you how to do vector multiplication or how to do the vector dot production, how to do matrix. I'm here to show you where they're being used. So just in short, dot products or the inner product, the dot product of two vectors results in a scalar and is calculated as the sum of the products, their corresponding components. So there, I'll show you two applications of dot products here in data science. That first one is a cosine similarity, and the second one is the GNAI app or the RAG. So about the cosine similarity, it is a measure it is a measure to determine the how similar two vectors are. It calculates the cosine of the angle between two vectors, providing a similarity like from -1 to 1, like dissimilar to dissimilar to complete similar. Complete similar. For this, I would like to I would obviously love to show you an example, otherwise how would you understand, right? Netflix series, okay. It is used in recommendations, like most of the times, like in Netflix. Suppose the movie Avengers has a reading of 5 dimensions. Okay, Avengers. Avengers has a reading of 1, 2, 0, 3, 1. Okay, and now another movie that we don't know. Let's call it B. A movie B that has a reading of 2, 0, 1, 1, 1. Okay, and what are these vectors? They are nothing but vector, like turned into actions. This could be the action, the drama, the story, duration, actor, and so on. For this movie, this is also represents action, drama, story, duration, actor, and so on. Now, how do we decide if we should recommend the movie B to someone who has watched the movie Avengers? Okay, here we use the cosine similarity. The yes, cosine similarity. Oh, sorry, I forgot to write the cosine similarity. Yes. If when we will use cosine similarity, if the cosine similarity is high, we will recommend the movie. If it is low or negative, it means the movie is very different from Avengers, so we won't recommend it. Who knows, the person who has seen an action movie and this movie could be a romantic, right? So who loves action movie would not definitely love a romantic movie, right? Or maybe could, but let's just say he wouldn't. So here now I will show this math. So how do you find out? Okay, so this we have the reading for Avengers, then we have the reading for the movie B and Avengers. We'll do a dot product. We'll do a dot product here. Dot product of A and B. A is Avenger here, and B, so this is 1 to 2 plus 2 into 0 plus 0 into 1. Am I doing it right? Then 3 into 1, 3 into 1. Oh, we have 1, 2, 3, 4. Okay. Yes, 1. 3 into 1 and 1 into 1, and the answer should be 6. 2, 0, 0, 3. Is it okay? Oh yeah, sorry. So this is this is 6, not 4. Why, I don't know why I was thinking 4. Okay. Now we'll find out the magnitude of A and B from the Euclidean product rule. So the magnitude of A and B is we'll do it using Euclidean's norm. So A is 1 square plus 2 square plus 3 square plus 1, and it is let me do it. 1 1 1. Okay, it is 3.87 something. Similarly, for B, we'll again do this. 2 square plus 1 1 1 it should be 2.664. Okay. We have our readings, we have our results here. So why we are doing this? Again, time for another graph. Okay, let me show it right here. In the Euclidean norm, what we do is, suppose we have a point here, another point here, x1, y1, x2, y2. We calculate this distance using Euclidean norm. How do we figure out this distance? We figure out with the formula of root over x square, x2 minus x1 whole square plus y2 minus y1 whole square. That's how we get this distance. So we are doing the same thing here. Like we have we know the distance, right? That's how we find out the distance. So in here, the movie A is here. The movie A, this is the A movie, and this is the B movie. Okay, so using this Euclidean norm, we'll figure out if they're similar or dissimilar. Okay, this is the concept behind it. So for now, the cos theta equal to the dot product divided by magnitude of those two vectors, which is 6 divided by 3.87 into 2.64, which results in 0.58. In another word, 58%. So this movie B is 58% similar with Avengers. So there is a chance of 58% that the person or this movie B will also be recommended. Okay, so that's how the whole recommendation product is used. Okay, process is used. So as you can see, this is also a work of vectors, some dot products, some cos theta, cosine, as I said, cosine similarity, and then these methods, Euclidean norm, these all are a vector calculations, vectors operations, right? So another example I would like to show is the RAG. Okay, the vector database. So when we talk about the vector database, we normally refer to the RAG, which is retrieval augmented generation. RAG. If you are not into machine learning yet, maybe you are still unfamiliar with this one. Don't worry, you should start studying it after clearing all this maths. Then that's how we will know stuffs. Retrieval augmented generation. Okay, so I'm going to explain it with a situation. Suppose you have a book. I'm going to change the color. not the purple one. Yes. Suppose I have a book or a PDF or whatever. It could be anything. This has like 10,000 pages. I don't know why it has this much pages. Maybe this is a history book. Anyways, so suppose I have a book of 10,000 pages and I want to create a chatbot. I want to create a chatbot which will be built based on the book, this book. And whenever I ask it a question, it will, without any delay, present me the answer of my question from the book. So now I will turn this book into vectors. Okay, I'll turn this book into vector. From book to vector. The color is so nasty. Okay, this is the vector I made. I just created. Okay, so now this book is in its vector form. This is the vector form. My work is done here, like the turning of vector. So for doing this, there are multiple techniques. There are multiple techniques of doing this. We have bag of words. Something is called bag of words. Then we have TF, IDF. Sorry, TF, IDF. Then we have word to vec. There are many techniques to and so on. However, once we convert this book into vectors, we will save it inside a vector database. Now time for a database. Let's do a database. This is a database. Okay, now from the user side. Okay, now we will look at the user side. This is my user. This is my user using a phone. Whenever I will write a question, the query will be converted into a vector. Okay, this query, it will convert into a vector, and it will get queried into the database. Once we query this into the vector database, like when it goes here, and we already have the informations here, a cosine similarity search will occur internally. Okay, then we will compare this vector. We will compare, like we'll do the cosine similarity. We'll do the cosine similarity, and it will compare the vector, the question we asked, with the another vector from this database. Okay, so this is our question, and this is something that it has found similarity of 98%, and this is the highest. This is the highest similarity it has found. So it will so the entire matching vector will be converted into text. After that, it will return and be displayed. Okay, so this was another example of vector being used in database. This is nothing but a vector. Again, it's all vector. Moving forward, now we have done the vector. Where is the list? Yes, scalars and vectors done, dot product done, cosine similarity done. Now we will move to matrices and applications. Okay, so let's do it here. Vector database. Okay, what was it again? Matrices. Okay. So we all know what a matrix is, right? A matrix is a rectangular array of numbers, symbols, expression arranged in rows and columns. We have rows and then we have columns. And this is a number, this is another, this is another. Okay, this is a 3 by 3 matrix. These are the columns and these are the rows. Okay, so what does matrix do in data science? First of all, data represents data. Okay, I will again show an example. Just a student's different marks, math score. Okay, math, then we have physics, and then we have biology. Okay, so maybe the first student got 55, 60, 65, 70, 60, 80, then 65, 45, 10. Okay, these all are vectors. Okay, these are a vector, right? You know that this is a collection. Like, by this you know that this is a collection of numbers, that is a vector. And this will converted into a matrix. If we converted them into a matrix, it will be like this: 60, 65, 70, 60, 80, 65, 45, 10. Okay, this represents a vector, and this represents a matrix. This represents a student's database, like grade sheet. These are the features. Okay, and this is a 3 by 3 matrix. So you can easily represent data with matrix. Like, I know I have shown a really silly example, but trust me, in industry this is heavily used. I will soon show you another example, but now I would like you to show I will go to the real life example later, but image. Okay, image in computer vision. This is interesting. Okay, do you know how our images do you know our images are made of pixels? We have pixels here. I'm not going to draw this. I would rather show you visually. Okay, so what about this example? this one. This one looks good. This one looks good. Okay, so as you can see, these numbers, okay, these numbers, they, like, in a picture, these a picture is formed by these layers. Okay, we have a red layer, a green layer, a blue layer, and what is the process here is this number gets added with this one, then this one, these 4 7 8 2 6 3 3 7 6, they are like having a addition operation, and that's how an image is represented. Okay, I'm really not getting a good example here. It's hard for me to describe in this way. But it was such a nice one. I wonder what happened. Verting. No. This is the code. I don't need it. I don't need this one. Okay. This one looks good. Okay. Anyways, so behind the picture, this is the actual drama that's happening. A lot of addition operations and so on. This is if you're related with grayscale, you will know what I'm talking about. And if you're not related with grayscale, we have a range of 0, which is black, to white, which is 255, if I'm not wrong. So this is the grayscale, and an image is composed of different numbers, like as I showed you. Maybe, yes, there were numbers, if you can remember. This is a very small one, a very small tiny picture, and it has numbers like 0, 128, 255, 255, and so on. Okay, these numbers, they what do you think? Our machine can understand this? No. These numbers, this pixel number, they are converted into a matrix. Okay, they are converted into matrix, and this matrix, this one does the main job. Okay, this one is the real hero here. Another important, like, first of all, it was the data representation, which I showed you here. The data representation, like this one, it was specifying 3 features, and for representing the whole matrix we use I and J, which is row into row cross column, and we may have 10,000 rows where we can easily arrange them through their features. And then we saw image in computer vision, like images are made up of pixels. Each pixels has its own code for colors, and images can be represented through matrix. We just saw it here. Then confusion matrix, like this one is the, like, whenever we build a machine learning model, whenever a machine learning model whenever we build a machine learning model, we always do the confusion matrix at the end. And confusion matrix gives us a percentage of accuracy, like how accurate our model is. Okay, so the confusion matrix is basically a matrix, like I have really just written here. And this matrix is a 2 cross 2 matrix. Okay, this is the matrix. The confusion matrix is a 2 by 2 matrix. Like usually it is made of 2 by 2 matrix. I'm showing you, don't worry. So the first one is true positive. The first one is true positive. Yes, the first one is true positive, and this one is false negative. Like this value represents false negative. Then here we have false positive, like it is positive but the result is saying that it's false, something like that. It's true for all of them. And then we have true negative. Okay, so to figure out that so how does this work? Okay, this is we first of all we take out the addition here for the true positive and the true negative. We first find out their addition. True positive plus true negative divided by true positive plus false negative plus false positive plus true negative, and that's how we find the accuracy of a machine learning model. This could be 50, like 50, 10, then 5, 31, like with numbers. Okay, and then this was the third example. Now for the fourth example. I suppose you know what is neural network. Matrix is heavily used in neural networks. Okay, let me show you a very simple neural network. This is a node, this is another node, this is my input. Okay, let's say it's x1 input and this is x2 input. This will be connected to another layer. Okay, and finally this is our output layer. Okay, this is our output layer. So These are connected here. This x1 is connected to this one, to this one, to this one over here. This one is also connected here, here, and here. Okay. And finally they are connected to this outer layer, and that's how we get the output. Okay, so there is something called forward propagation here, which is also connected with linear regression. And matrix is used in neural network because neural network is all about hidden layers, forward propagation, backward propagation. And in forward propagation, what we do is we use the transpose of weights of the layers here. So what are the weights here? Okay, the weights are this has a weight w1, w2, w3, w4, w5, w6. These are the weights. Okay, so the forward propagation for the forward propagation, we use the transpose of these weights, and then we multiply it with x, because we have 2x here, right? And here we have 3 weights, right? So it's basically 2 into 3, like, right? A form of matrix. Okay, and here these are our biases. Okay, these are our biases, b1, b2, b3. It gets added later. Like, it is similar to the mx plus c formula. And what is w here? What is w indicating here? You will be amazed to know that w is nothing but a matrix. Okay, w1, w2, w3, 4, 5, 6. This is a matrix, and we are using the transpose of this matrix, then x. What is x? X is also x1 and x2. See? And for b, like, these are getting added, right? It will transpose, and then b, for b is biases, b1, b2, b3. What are these? These are all matrix. So I have shown you one hidden layer here, but in reality there are thousands of hidden layers in a neural network. So you can guess like the importance of matrix in a neural network. Like, all these are basically matrix multiplications, right? So matrix is also used in regression, like for the formula y equal to mx plus c, where m summation of mx plus c, where m could be m1, m2, and x could be x1, x2. These are just some basic examples. If you don't know about neural networks yet, that's fine. I just wanted you to show where matrices are used in data science. And in NLP, it is also used in NLP. Okay, like this was the 4th example, and I'll show you just another example that is for the NLP. For NLP, and I will of course I will present you another real life example. Let's say I have a data set with two features: review and positive or negative. Okay, pos or neg. This reviews, like, it could be the food is good. The food is good. This is a positive review. This is a positive review, so I will give it a 1. The food is bad. This will get a 0. Okay, this is our data, and this will get turned into vectors. Like, we can convert the text into vectors. And the food is good. Okay, like for this, the food is good. This could be, for this one, we can this might represent 0 to 4 1, and this one, it might, sorry, and for the second one, whatever, I'll just put some random numbers here, 2 4 3 4, whatever. So we have set 0 for a negative review and 1 for a positive review. So after combining all these reviews, our collection will look like a matrix. Okay, right? This is literally a matrix. 0 to 4 1, then 2 4 2 4 3 4, which is 1. This is 1 0, and here we can use another bracket. So our model here, this is our model. We will input here, and NLP will run some analysis and then we'll get a sentiment analysis. Okay, so matrices are everywhere, as you can see. Now we are done with these examples here. What was the last thing? Okay, we are already like close to the end of this video. Matrices and applications are done. These 4 are done, and then matrices operations. Okay. Okay, for a review, for short overview, examples of matrices in data science was data representation, image in computer vision, confusion matrix, neural network, and NLP. Like the three, like the last 4, the last 3 was the main core of machine learning, and their matrix operations were the fundamental of these processes. So I hope you realized how important is matrix, and like these operations are very fundamental to data science because they provide you the mechanism to manipulate. I don't know why I choose this color. This is so gross. Okay, so they provide you the mechanism to manipulate. Then matrix addition, add or subtract the corresponding elements of two matrices of the same dimensions. Then scalar matrix multiplication. Scalar multiplication involves multiplying every element of a matrix by a scalar value. So let's say we have a matrix that represents we have a matrix representing product prices in dollars, and we want to adjust these prices for inflation by a factor of 1.05. Now if you want to adjust it, we have to perform scalar what's happening? Okay, scalar multiplication. We have to perform scalar multiplication here. Now if we want to adjust it, we have to perform the scalar matrix multiplication, and this factor will get multiplied to every element. Thus we will have an adjusted prices based on inflation. Now for this real life example, like it was already a real life example, but still okay, I'm out of space here. Maybe let's remove this. Perfect. Yes. Okay, so I will show you a data set. Of an IT firm where we have the base salary of engineer, and then we have the base salary of HR, and then the CEO, receptionist. Okay, let me remove this one. Receptionist. Okay, we have the base salary of a receptionist, HR, and CEO of a IT firm. So it could, let's say this is X, Y, Z, and so on. X, Y, Z, and so on. There could be many more people, of course there are. And we have, let's just say we have 3 columns representing the base salary of this receptionist, HR, and accountant, CEO. So in 2025 we are facing an inflation of 8%. Now how will I adjust all the salaries? That's where scalar matrix is used for efficiency. I will multiply the whole matrix this whole matrix with 0.08 and we'll get an adjusted salary. Okay, so yeah, I mean, if you think about this, like a simple scalar matrix, this is just a simple scalar matrix, but how important is this, right? Like the use cases of these things, like they're mind blowing. This is really amazing, guys. This is really amazing. And finally, we have the matrix multiplication, which involves the dot product of rows of the first matrix with column of the second. Okay, let me write it. Let me write it for you. Okay, so we have a matrix. The first matrix is A m into n, and the second matrix is P n into P. Okay, so it involves the matrix multiplication. It involves the dot product of rows of the first column and with the column of the second matrix. Okay, this result is m into P. Okay, oh, I'm extremely sorry, this is not this one. I got confused with the rows and columns. Okay, so involves the dot products of rows of the first matrix with the column of the second matrix. Okay, so the result is m cross P. Okay, the first matrix column should and must be equal to the second matrix row number. Okay, this is also another extensive operation into the world of machine learning. So this was it, and yeah, I hope you have enjoyed this video. Comment down if you have any other problems, and I hope to see you all in my next video. Thank you.